My name is Leo Hickman. I edit a website called Carbon Brief, and we specialize on reporting and analyzing the latest climate science and also the related policy response to that science. We've often reported on Freddie's research coming out of the Environmental Change Institute at Oxford University and other scientists as well who work on this particular specialism within climate science around extreme event attribution science. But I'm going to hand over to Freddie now, and then Freddie and I have a bit of a conversation, and obviously we'll want to take some questions from the floor. But Freddie, I'll let you take over. I might just sit down here. It'd be a bit weird me sitting on that stool.
Yeah, thank you very much. Thank you very much for inviting me. I'm Friederike Otto. I'm the Deputy Director of the Environmental Change Institute at Oxford University. And I work on extreme weather events and on the attribution of extreme weather events. And the project that the BNP Foundation funds is also on that, and I will finish with a very brief overview of what the project is about, but mainly introduce what the science is about. So we know, and we have known at the latest since the first IPCC assessment report in 1990, that anthropogenic greenhouse gas emissions are increasing global mean temperature, and the attribution of global mean temperature to anthropogenic greenhouse gas emissions is something that has been, the methods to do that and the knowledge about that has been around for many years. So that is not something new. And this is just, just a reminder what we do when we attribute long-term trends like global mean temperature. And what you can see here is all these black dots are observations of global mean temperature from the 1860s onwards. And what we want to do when in attribution is that we want to know that we want to explain the drivers behind what we observe. And so in this case, here you can see that there's an orange curve and a blue curve. And the orange curve is the response of the climate system, so global mean temperature, to all the known human forcings. And forcings, external forcings are things that are outside the climate system. Human forcings are greenhouse gases from fossil fuel burning. It's also aerosols, which, also from land use and fossil fuels. And the natural external forcings are things like sulfates from after volcanic eruptions, changes in the solar cycle, and so on. And what we do in this type of attribution is that we model the climate system response to all the known human forcings, and this is the orange curve that we see here. And we model the climate system response to all the known natural forcings, which is the blue curve that you see here, and you can see the dip here. This is the last big volcanic eruption from Mount Pinatubo, so you can see this very clearly. And what we want to do when we attribute this is to find the best fit combination of the two that explains the observed trend. And this is the red line here that you can see. And what we need to do, we can't just use the emissions, but need to go through this modeling step is, we know very well what the forcings are. So we can measure the emissions from greenhouse gas emissions. We can measure the volcanic eruptions. But so we know what shape these curves need to have. So when there need to be dips, but we don't know the exact size of that. So it could be that it actually should be a bit higher, or that this curve should be steeper or flatter. And in this attribution step, we identify what the shape is and then find these best fit combinations. And if there were forcings we had forgotten about, then it wouldn't fit. Then we would not find a fit. So this is what usually or historically has been talked about when people talk about attribution, and that is, it's relatively straightforward. You don't need any complicated climate models. You can do it in a model that you can make on your Excel spreadsheet, and you just need the observations to do that. However, to quote my colleague, global mean temperature doesn't kill anyone. The impacts of anthropogenic climate change are not directly through global mean temperature, but mostly through high impact extreme weather events and also sea level rise in combination with storm surges. And so this is just a figure of the records that have been broken, very large records in terms of heat waves and storms, droughts, and rainfall events just from 1 year, the year 2015. So just an example of this is how many record-breaking extreme events there were that had very large impacts. So the question is now, are these extreme events, is that climate change or is that just wild weather? Because extreme weather events have always happened, the records have always been broken, and the longer the record is, then yeah, it will be broken. That is basically what the science of extreme event attribution is trying to look at. Until that science has been developed, which is more, well, it has been suggested 10 years ago, but really only in the last 5 years, a lot of research has been done in that field and all the methodologies have been developed. And before that, whenever an extreme event happened, it was still that people asked the question, what's the role of climate change? Is climate change playing a role? And there were two common assumptions that have usually been said. The first one was that, well, all extreme weather events are made worse by climate change, which is not the case. What is true is that all extreme events are happening in a changing climate. So you can say that they are all affected, but that is trivially true and doesn't tell you anything about the severity of the event and what to expect in the future. This is just examples after Hurricane Sandy. And also, this is from the UNFCCC. They have a website where they say, everyday climate change, and people just post photos from weather. The other assumption is that a single or an individual weather event cannot be attributed to anthropogenic climate change. And one prominent person who said that in his first term in office is that guy. But in the second term in office, he said that was actually not true anymore, because now the science has evolved and we can attribute individual weather events to anthropogenic climate change. I've said already that extreme weather events have always happened. And if you boil down to it, every extreme weather event is ultimately unique, and it's always a combination of different causes, external forcings, just internal noise in the climate system. So it will be impossible to say that an event could not have occurred without anthropogenic climate change. However, what we can say is how the risk of an event occurring has changed due to anthropogenic climate change. And the reason why I have these dice here is because the main methodology behind the science is very straightforward, and it's a bit like rolling a dice. So when you roll the dice and you roll it 10 times, and 8 of these 10 times you roll 6, then you can say, if you play the right game, well, I'm really lucky. But if you roll it 100 times and you find out that 70 times of these 100 times you roll a 6, then you might get a bit suspicious that this die might not be a normal dice. But in order to find out from just counting the eyes on the dice, you have to roll it many, many times to be able to, just from your observations of the dots, to work out whether or not the likelihood of a 6 occurring is 1 in 6, as it should be with a normal dice, or if it's something different. And that is basically the same what we do for extreme weather events. So what we want to know is, given the current climate conditions, so with the current concentration of greenhouse gases in the atmosphere, what is possible weather in the world we live in? And so let's say the extreme event we are interested in is an extreme rainfall event in southern UK in the winter, and then we want to know what are possible rainfall events in southern UK in January. And we can simulate that, and then we will get, maybe like in the schematic, a distribution of possible rainfall events, and then we say everything above this threshold, maybe that's the height of the levees, or is what we call an extreme weather event, and so you have the likelihood of an extreme weather event occurring in the world that might have been. With the die, you have the huge advantage that you know that a normal dice has a 1 in 6 probability for each of the numbers to come up. With the weather, we don't know what the likelihood of an event occurring without anthropogenic climate change will be. So we have to simulate a counterfactual world, so a world without anthropogenic climate change. And that's exactly what we do. So we repeat exactly the same experiment, remove the anthropogenic forcings from the climate models that we are using, and then simulate what is possible weather in the world without climate change. And in this schematic, you might get a very different distribution of possible rainfall events in southern UK, and you look at your same threshold and have a very different likelihood of the event occurring. And in this example, you could then say anthropogenic climate change has increased the likelihood of the event occurring. So this is, of course, just a schematic. And this is the most extreme example I could find in the literature of where climate change really totally changed the distribution of the event. And that is for extreme annual mean temperatures in Australia, where we have exactly the same as you've seen before, a distribution of what are possible annual mean temperatures in the world we live in. And so this here is the observation of 1998, and this is the one of 2013, which is directly before this paper has been published. And we can see that in the world we live in, the event was actually not that extreme because it's relatively in the middle of the distribution. Whereas in the world that might have been without anthropogenic climate change, well, in this simulation, you actually don't get an event at all as the observed one. So in this case, you would say it was almost impossible without climate change to get an event like this. But of course, annual mean temperature is also not really what causes the direct impacts. And usually the high impact events are a bit more subtle. And so this is the only unfriendly graphic I have, which is a nice way to present small changes in the tails of the distribution. And if you're a hydrologist, you know this and you love this because it's a return time plot. If you're not a hydrologist, you probably have never seen it. But it's basically the same as the other graphics I have shown before, just a different way of presenting it. So these red curve here is lots and lots of red dots. And each one of them is one simulation of possible rainfall in January in southern UK in 2014 in the world we live in. And so you can see, that, and here we have the magnitude of the event, and here we have the return time. So every 50 years in the world we live in, we expect to see January mean rainfall above 4.4 millimeters. Every 100 years, we expect to see about 4.8 millimeters or higher. So this is how we read this graph. And the blue curve, the dark blue curve here, is the simulations of the world that might have been without climate change. And so if we now observe an event that might have almost 4.48 millimeters per day of rainfall for the whole of January, which was a record-breaking event at the time, then we can say that in the world that we live in, an event like this has a return period of 1 in 100 years. So that is every year we have a 1% chance of seeing an event like this in January. And we can then say, look at the world that might have been, and either say, well, the same event, so the 1 in 100 year event, would have had a magnitude of only 4.6 millimeters per day in the world that might have been. So you can say that anthropogenic climate change has increased the magnitude of the 1 in 100 year event by 0.2 millimeters per day in this case. Or you can look at an event of the same magnitude and say, in the world that might have been, what would have been the return time of this event? And this is here about a 1 in 130 year event. So you can say that anthropogenic climate change has increased the likelihood of the event as it was observed occurring by 40% roughly. This is a graphic that Carbon Reef has made, and they have actually put a huge effort in earlier this year to put together all studies of extreme event attribution that have been made basically within the last 5 years. And it's about 140 studies that are on this map. So you can see there are some continents where there are very few studies, but in Europe and in the US, there are quite a few studies. And here the orange ones are the ones where climate change was found to have increased the likelihood of the event to occur. The blue ones are where climate change was found to have decreased the likelihood of the event occurring. And the gray ones are the ones where the results were inconclusive. And it is very, very important to stress that this is not representative of all the events that have happened. We are very, very far from having an inventory of the impacts of climate change on extreme weather events. But this is just an overview of the studies that have been done. And most studies are done because they happen in the backyard of the researchers, or because they have, for whatever reason, people are interested in them. But it's not in any way a representative or comprehensive process to pick these events. And so while there are two ways of how climate change affects weather. One is the so-called thermodynamic effect, that is when we have more greenhouse gases in the atmosphere and we have higher temperatures, then we expect on a global average the likelihood of heat waves to increase, cold waves to decrease, and a warmer atmosphere can also hold more water vapor, so we expect more intense rainfall events on a global average. But there is a second effect, and that's the so-called dynamic effect, and that when we change the composition of the atmosphere with more greenhouse gases, more water vapor, that also affects the atmospheric circulation. And which means that where weather systems develop and where they travel, so for example, for the UK, the zonal systems in the winter that bring in the rainfall, we might get more of them or fewer of them, and that can, it can be that it intensifies the thermodynamic effect, or it can also be that these two effects cancel each other out. And so you don't actually have a change in the likelihood of an event occurring because of anthropogenic climate change. So there are always four possible outcomes a priori for an attribution study. It can increase, decrease, not change, or with our current understanding, with our current tools that we have available, with current observations, we can't say. A crucial step in this whole process is to determine what is actually an extreme weather event. And however you define that, you will get a different outcome of your attribution study. There is, in most cases, no right or wrong definition, but it totally depends on who's asking the question and why are you asking the question. And this is just an example of a heat wave in Serbia we looked at in one of the very early studies, where when you just look at the temperature in the summer in the region where the heat wave has occurred, you can see that the heat wave was about a 1 in 100-year event in the world that might have been. And in the world that we live in, it's a 1 in 10-year event. So you can say that climate change made the event occurring 10 times more likely. However, when we look not just at the temperature as a definition of the heat wave, but at heat stress, which is a combination of heat and relative humidity, basically what's affecting the human body, you can also see that climate change increased the likelihood of the event occurring. But the magnitude of this change is quite different. Both results are scientifically correct. It's not that one is the right way to define a heat wave and the other one is the wrong way. And if you're a health official, you might be much more interested in this one. But if you have agricultural business or so, then the pure temperature might be what is really what is affecting you. And of course, we don't have just the meteorology that defines an extreme weather event. Whether or not an event has impacts totally depends on who is in harm's way, so vulnerability and exposure, what are the assets. And this was one example of a drought in Sao Paulo in 2014 that we have studied, where we found that when we just looked at precipitation, and then we also looked at P minus E, which is precipitation minus evaporation, so from a meteorological point of view, the water availability, and found that, first of all, it was a 1 in 10-year event, so not from a meteorological point of view, not very extreme. And actually, looking at the observed record, we found very similar events in 2001 and in the 1970s. And we did not find that climate change changed the risk of this event occurring. And then we also looked at population and which is the red curve here, population increase in the area, and a particular water usage in the area. And you can see that while the meteorological event does not change, the water usage almost changes exponentially in the last 20 years. So a drought that the population could have coped with 20 years ago is a drought now that has very large impacts because of these changes in vulnerability and exposure. And that is the project that the BNP Foundation is funding is to apply these methodologies in South Africa. So we work together with a team of researchers at Cape Town University on looking at the recent droughts and floods that have occurred in South Africa, and not only look at the changes from the meteorological point of view, but also look at the hydrology and economic impacts, and also try and address these questions of what's the vulnerability and exposure doing in order to be able to assess how risks are changing as the combination of the hazard and the more societal changes. That's me done.
So I will take up my stall now. Thank you, Freddie. I just wanted to, before we take some questions from the floor, I just wanted to ask you to expand a little bit more on the different types of extreme weather events. So on some of your earlier slides, you talked about heat waves, you talked about extreme rainfall events, cyclones, hurricanes. Can you just explain a little bit, is there a difference in terms of your work between those different types of events? Are some easier to study and attribute related to climate change, or are some more challenging?
Yeah, definitely. So one of the, when you do an attribution study, one of the key steps is to look at how are climate models able to reliably simulate the kind of event that you're interested in studying. And while we have many climate models that are able to reliably simulate heat waves, at least in many parts of the world, and to simulate, especially in mid-latitudes, rainfall, it requires more complex, more expensive climate models to look at things like hurricane, for example. And there are events like tornadoes or flash floods that occur on spatial scales that are much smaller than what the resolution of even the best climate models you have can resolve. So that would be, we can't really look at flash floods at this point in time. But it's very, you have to, for each event that you're interested in studying, you have to do this evaluation because some climate models might be really good at representing rainfall in Britain, but a very similar event in, say, South America is not well represented at all with the climate models because it does not capture the atmospheric processes. So it not only depends on the type of event, but also on the region as well.
So there's a very interesting sort of strand of your research, which is the rapid event attribution work, where within a matter of a few days after an extreme event, say a big flood in the UK or a big heat wave, you will actually produce preliminary results very, very quickly, almost within, as a journalist, kind of within the news cycle. So as everyone is talking about it in a country or in a region, the politicians are talking about it and we're saying we must do something, you can publish results incredibly quickly, which is actually very unusual for science. Normally you go through the peer-reviewed journals and it takes months and months and months. Can you explain a little bit about how you're able to do that, and then the relevant, why you do it so quickly, i.e. is it because you want to have pertinence and relevance for policymakers and insurance industry, et cetera, et cetera?
I think the why is very simple, because when extreme events happening, people do ask the question, what's the role of climate change? And people will ask the question for so long until they get an answer. And if there is no scientific answer, then someone with an agenda that is not a scientific agenda, but a political agenda will give an answer, and we have seen that quite often. So, at the aim of providing scientific evidence within the news cycle, that's a bit flexible term, but it is to avoid that and to say, well, there is no evidence, or the evidence saying X, Y, and that. And the way how we can do that is, so in our rapid studies, we only use methodologies that have been tested with cases that have gone to peer review, and we use, so we use model simulations that we compute in advance. So, for example, one of the main modeling climate modeling type that we are using is a so-called atmosphere-only model. That is one that does not have an ocean, but just computes the atmosphere. And so it needs to be given observed sea surface temperatures. And instead of waiting for the observations of the sea surface temperatures to be there, we use seasonal forecast temperatures to drive the model, which are for almost all purposes good enough, close enough to the real observations that we can run our models in advance. So we have always the simulations for the next 3 months available in advance, and so can then quickly look at them. But the key ingredient is that the people in our team have done that many times, know each other well, and know what they are doing. So that has actually turned out is the key thing to be able to do rapid attribution studies, that you have the experienced people.
And is there some, again, back to my earlier question, are there some types of events that you can more readily do those rapid, or are some just more challenging and you can't really do them that quickly?
So, for example, we, because of popular demand, we really wanted to do an attribution study on Hurricane Harvey quickly, and we have done a study, but we have submitted it for peer review, and it has actually been accepted and will be published next week. But because hurricanes is a type of event where you need very different climate models than the ones we usually use in our team, so we had to work with different colleagues around the world with using different models, and so we basically, the methodologies were not quite developed yet, but we had to do model development, and everything where we need to do methodological development, we can't do quickly. So basically events that we have done before, but just happen in a different part of the world or different time of year. So that's something that lends itself to rapid.
So it's quite a relatively young branch of climate science. I think from memory, I think the first paper that I can think of was from 2004, which was a study of the fatal heat wave in Paris, or struck the Paris region in 2003. And I think Peter Stott from the Met Office and your colleague Miles Allen were involved in that paper. And I think from memory, you can correct me, but I think the result of that was that the human influence had doubled the chances, or made it twice as likely. So from that moment, sort of 13, 14 years ago, up to today, and then looking forward for the next 5 or 10 years, where do you think the biggest opportunities or maybe challenges for this science are in terms of the next 5 or 10 years? Do you need faster, bigger computers, or is there, where are the sort of challenges and priorities for you now?
I think the main thing that we need is actually people. So yeah, you're right. The first paper was in 2004, and that found that climate change at least doubled. So which is the at least is quite important. So that's not the best estimate, but they can exclude that it had an influence that was less than doubling. And then it was very quiet for a few years then, and really the field has only started to develop since probably 2010 after the Russian heat wave, because after the Russian heat wave there were 2 papers published in 2011. One that said that climate change made the heat wave 5 times more likely, and the other one said that climate change did not play an important role. And so that, of course, that was not good to read that, and people were saying, well, oh, this is really contradictory. But then it turned out it actually wasn't, because they looked at 2 very different ways of defining the event, and they were both correct. But the fact that needed to be pointed out in the scientific literature led basically to a huge interest in this field of research, and more researchers started to look into this, and then that really started the different methods to be developed. I think so. Now that we have shown as a community that we can do these things, obviously also the demand is quite large. So I think in the next 5 years, there will be the attempt to really, so our rapid attribution is always dependent on, well, do we Do we have time to do it? We are not an operational service. We are researchers. We have other things to work on it. So we have really only done it on a few occasions. But so definitely in Europe, the Met services are demanding that they are able to operationally access attribution information, because they get questions from the people who they normally provide their weather services to. These people demand attribution information. And so I think in the next 5 years, there will be the need to in some way develop an operational attribution service. And I think the key thing that is missing at the moment is that it's still a very small community, that very few people who work on this, and it's particularly in developing countries that there are very, very few. So, but you only realize which methodologies or what you can't do when you try to do it. So I think we need to work more on events that are, we know quite well how to do floods in Britain now, but but we don't, for example, know how to do heat waves in India, which sounds a bit strange, but because in India you have not only greenhouse gases in the atmosphere, but you have very localized strong influence of aerosols from just air pollution, and that has a strong influence on the temperature. And so the observations don't match the climate models. So there is a lot of research that still needs to be done, where the methodologies in principle exist, but the people to actually apply them are not. We don't quite have them.
With say your analysis of an extreme rainfall event here in the UK, in a rapid attribution result, you might be able to get out 2 or 3 days later, maybe, or a bit. Is that?
No.
You've done that, right? You've done it that fast, I think.
We have done, the fastest we've done was the storm Desmond, which happened 2 years ago, where the storm happened on the 5th of December, and we had the results on the 10th.
Okay, well, that's pretty. So is in that instance, is it manpower or humans, to join the effort, or is it you just need faster computers to make it 48 hours that you could do it?
It's manpower. There are. Yeah, so the steps you have to go through in an attribution study is, first of all, what happened. So you need to look at observed data, and quite often it's very hard to get real-time observations. So that can be something where it already falls to pieces to do anything quickly. The next step is then to make an event definition. So what is it actually that has caused the impact? So if you have flooding, for example, was it a one-day extreme rainfall, or was it actually that the whole season was very soggy and it was just that the last little bit of rain caused the river to flood, or was it rainfall somewhere more upstream? So what is the spatial and temporal dimension of the event? And that's always a trade-off with the definition of what caused the impact and what climate models can simulate. And that is just something which requires, first of all, local expertise. So you can't do an attribution study without having someone who knows the local meteorology. So we wouldn't be able to do an attribution study for flooding in Bangladesh without the Bangladesh Met service to not only provide the observational data, but also just the knowledge of what is the key aspect of that event, so that we have a meaningful event definition. And then we need to do the model evaluation step. And that is something that, if we had a clearer protocol of how to do that, that could be something that could be sped up, which is something where there is definitely potential to just have something a bit more systematic, automated, which could speed the process. And once you have decided which models you can use and which you can't use, then you calculate and you do this thing, so you calculate the change in probability with the different methodologies. But you would never use just one model or just one methodology, because all models are wrong. So you would want to be able to compare them to assess the confidence in the results. And so the step after computing the probabilities is what we call the synthesis step. So looking at the results, making sense of them. And that, I don't think that can be really sped up, because that just takes time to understand.
There's never going to be a day, you think, where we're watching the TV one evening and the weather presenter is saying there's a big storm coming, and we now know already that this is twice more likely, because it's not going to be real time. It's always going to be probably a few days
Definitely
later.
Not in the next 5 years. Maybe in the next 50 years when, well, you have now that people do weather forecasts. There are just an enormous amount of people who know how to do weather forecasts, who know how to interpret on a daily basis the weather ensembles. If we had the same more attribution, then it could also be that quick. But we are very far from that.
So I guess I'm asking that because I'm interested in, I guess a lot of people in this room are interested in the utility of your science. How are we going to materially use your results and your scientific kind of discoveries and etc. in, I don't want to use the term real world, but in terms of how is this going to be used? So I can already think of like an insurance industry finding your research very, very useful and interesting. Maybe people in the banking sector might change their view on lending on a certain project in a certain country or a certain region if they look at some of your curves going up for the probabilistic sense of some of these extreme events. I think if I'm a lawyer, and I'm not, I'm kind of very interested in your work, because I'm thinking, if I'm wearing my litigation hat, I'm thinking, can your work be used in a courtroom to attribute blame on a certain extreme weather event and all the damage that results from that? Can that be coupled with some of the other scientific work, other climate scientists who are working out who is responsible for certain percentages of emissions going into the atmosphere? So is one big corporation or one country responsible for X percentage of emissions going into the atmosphere over a 1, 10, 100-year period? Therefore, combined with your work, can they say this corporation or this country is responsible for a percentage of that damage? Do you see what I mean? I'm just wondering. So when are you going to be called into a courtroom to present evidence as an expert witness in a court case?
Well, just having been last night on a panel with 4 experts from the legal community just talking about that, I'm not sure anytime soon, but that's not really for scientific reasons, but more because it seems that courts are struggling generally with scientific evidence, no matter what kind of scientific evidence. But I'm absolutely not a lawyer, and you might probably be lawyer, so I should not talk about the legal aspects. But we have actually done what you have suggested for where we have looked at the emissions from individual countries, how that affects global mean temperature, so potentially, and how we can combine that with the attribution. And we have looked at an example of a heat wave in Argentina, which was made 5 times more likely in total due to anthropogenic climate change, and then looked at what individual countries have contributed to the increase in likelihood. And so from a scientific point of view, we can absolutely do that. But you have, there are some choices you have to make. So for example, when you calculate the emissions per country, do you only calculate the emissions that have been really occurred in that country, or do you include the ones that have been occurred when products have been made in China that are actually consumed here? And whether or not you include that makes a huge difference. And then you can say that in these cases, when we look at the overall effect of climate change, we always look at since the Industrial Revolution, so since climate change began. But when you want to say for a country being responsible of their emissions, you can't really blame a country for emissions in 1850 when nobody really knew about climate change. So you could say you only count the emissions from 1990 onwards, when the first IPCC report was published. You can do that, what you, when in the time you start is, has a strong influence on the outcome of the numbers that you come up with. And these sort of more moral choices have a much larger influence on the result than the scientific choices of which methodology you use.
Mm-hmm. Okay, I think it's probably a great moment to open the questions out to the floor. So I guess if you want to put your hand up and quickly say who you are and then address your question to Freddie. But we obviously have a question here. Are these microphones?
Yeah, should be on.
Okay, yeah.
It's I think just for the video. I think we can hear you.
The question is the models you look at sound like they are reactive, not predictive, or you just calculate the probabilities which can be used in prediction. So on top of this, are you developing something which can be used in predictions as well? And second, are you collaborating, or you plan to collaborate with the decision makers or policy makers around the globe?
So the models we use are exactly the same models that are also used for climate predictions, and the same methodologies that you use for attribution, you also can use. One of the key steps in the attribution is to estimate what is the likelihood of the event occurring today, whereas today does not mean today on the 8th of December in 2017, but today is sort of the 10-year time horizon. So that, and then with the same methodologies, we can also look, well, we have now 1 degree of additional warming. How does the likelihood change with 1.5 degrees, with 2 degrees? So the methodologies are exactly the same, and we have done that. So yes, with the attribution step, you have the huge advantage that you have observations as well that you can use to base your estimations on, and you can use statistical modeling on observations. That, of course, you don't have for the future. And well, yes, we do want to work with decision makers, and we have. So I have had several projects where we work with a very, 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 very small subset of some decision makers on how this kind of information could be useful. So we had a project in Kenya, for example, where we looked at the while the drought was ongoing, we did an attribution study on the drought, finding that actually anthropogenic climate change is not a game changer in terms of the risk of drought. So it does not increase the likelihood. It has not increased the likelihood in a significant way, which the Kenyan government we worked with, they were not too happy with that result at first, but then
Was that generally, or just that one specific event, or was it just generally heat waves? Drought. Do you say droughts or heat waves?
It was. We looked at
in Kenya.
That was for that particular drought that occurred actually at the end of 2016, and then we had a press briefing, and we developed a press release together with the Kenyan government, which was very tricky to say that climate change is not really. The press release needed to say that climate change is happening, which of course it is. But then our results showed that, but in this instance, it did not really change the risk of the drought.
Okay, so it was that particular event.
Not say in the press release that, so maybe there are some mismanagement. So that was tricky, but I think it was, so that is one aspect, that one example where we have really worked with decision makers and also try to be responsive, so do something where they had at the right time when they actually have the questions. But I think that is just a very small example, and there is a lot of research to be done of how to present this information, how to make this information so that it's actually useful. I think that's definitely more work to do, and one of the things that we are also doing in the work now in South Africa with BNP.
So presumably a key product or document that you will produce for policymakers all around the world is obviously the next IPCC report, the sixth assessment report, which I think is due in 2021 or 22 or something.
Working Group 1 is in 21, and
Yeah.
Working Group 2 and 3 will be in 22.
Okay. But way before then, next October of next year, there's going to be a special report which came out of the Paris Agreement 2 years ago, where the governments of the world specifically invited scientists in the IPCC to produce a special report looking at 1.5 degrees, i.e. one of the key goals that came out of the Paris Agreement was to keep global temperatures above pre-industrial levels, well below 2 degrees, but ideally below 1.5. Is your work around event attribution going to feature in that report next year, or is it more going to be, I guess, a much bigger part of the reports that come out in the early 2020s compared to the last one that came out sort of 3 years ago?
So compared to the last assessment report that came out in 2013, it will be a very big part of the 2021 report. So in the Working Group 1, so the physical science basis part of the IPCC in 2021, that will be basically the last 2 chapters will be on extreme, so the chapter 11 will be on extreme events and how they are changing across timescales, which is very much using the methodologies that have been developed around extreme event attribution, and then doing exactly what you said would be really useful to extend that to projections. So and there is the chapter 12, which should be about making, providing not only extreme events, but hazard information that can be used in comprehensive risk assessment, which will also be basically using that, combining it with hydrological modeling. And in the 1.5 degree report, event attribution is not featured as such, but the methodologies are used to assess changing risks under one. So comparing what are the impacts on under 1.5 degrees compared to impacts on 2 degrees, where you, if you only look at mean temperature or mean precipitation results, you don't actually see much difference. And when you see the difference, then it's relatively linear. So you could, so all the papers that have been published sort of before Paris, no one has looked at 1.5 degrees, but we have now actually using these methodologies identified quite a few places in the world where you see non-linear changes in extremes between 1.5 and 2 degrees, so that you have an increase in the risk from 1 degree to 1.5 degrees, which might be a 5 times increase. But then when you have from 1.5 to 2 degrees, you suddenly have orders of magnitude more likelihood in the risk.
I think we've only got about 5 minutes left, but maybe if we can take a couple of questions and then you can address them. So you've got a question here.
I was wondering, you were saying that you compare today's world with a theoretical world, which is if there was no anthropogenic influence. How do you model that? That was my first question. My second question is, can you tell us if Harvey was man-made or not?
Sorry, it was man-made?
Harvey.
I don't think I'm allowed to tell. There will be a press conference next Thursday, and I think I will be in trouble if I tell you.
Okay.
But actually, there is already one paper has been published on that, which uses more traditional methodologies, which said it was man-made, and yeah, we're not contradicting that. But I can't give you the numbers. So that was your second question. Your first question was, okay, how do we model the counterfactual, the world that might have been? We also look at the theoretical world we live in, because we use climate models. What we know very well, the concentration of greenhouse gases in the atmosphere that are due to anthropogenic sources. And so the climate models have external forcings that they are provided with at every time step. And so when we model the world we live in, then we use the observed concentrations of greenhouse gases as they are now at every time step as the boundary condition of the model. But since we know very well how much of this concentration is man-made, we can remove that and use this lower concentration as the boundary condition for the climate model at every time step in the counterfactual world that might have been. Of course, for the model evaluation, we simulate sort of 30 years of a time period where we have good observations so that we can compare the climate model with observations and see if it gets the right processes, the right statistics. We can't do that for the counterfactual. And so the uncertainties around the counterfactual are larger than the uncertainties around present day. But in principle, we know what needs to be done.
Okay, we'll have one last quick question here at the back, and then we'll probably wrap it up.
Real estate, BNP Paribas real estate. Well, we used to hear a lot about tipping points. What are the potential impact of tipping points on your research and these events?
Well, it depends a bit on what you mean with tipping point, where there's a...
the models go out the window. Potentially.
Well, tipping points are usually where you have sort of that a regime, it could be a weather regime, so yeah, disappears to exist, or some dramatic changes, and it could. So that is something that if it's a tipping point, like, okay, so for example, you in Northeast Australia, in a region where you used to get rainfall systems in the summer that brought in a decent amount of rainfall. But now, due to climate change, these rainfall systems actually bypass the continent completely, so there's no rain. That will be a tipping point, and you will pick that up. You would see that with these methodologies that we use. With other more dramatic tipping points when you have a complete breakdown of the North Atlantic circulation in the ocean, which is also something that would not tip overnight. That is something that you would not see in this, because it's not something that happens on sort of a 10-year time frame. And there to look at this, you would use completely different methodologies.
Okay, I think we probably have run out of time, but I just want to invite you to thank Freddie, and then I think Anne-Marie, or are you going to come back up and say a few words? No? But I think the plan is that after we've thanked Freddie, there are some drinks next door.